Assalamualaikum warahmatullahi wabarakatuh. My name is Nurul Najwa. I will explain our objective. First, calculate the normal and tangential components of a particle, velocity and acceleration as it moves along a curved path. 2. Using normal and tangential coordinates, solve the equation of motion. 3. Find the components of the velocity and acceleration in the direction of a vector. And last, find the components of acceleration along the tangent and normal. Background: when a particle moves along a curved path, it is sometimes more convenient to use non-Cartesian coordinates to describe its motion. Normal and tangential coordinates are frequently used when the path of motion is known. The origin of the n-coordinate system lies on the particle, the origin moves with the particle. At the time of consideration, the t-axis is tangent to the path, curve, and positive in the direction of particle motion. The n-axis is perpendicular to the t-axis and points in the direction of the curve center of curvature. We get a unit vector in the direction of motion from the unit tangent vector t. The direction of motion can be deducted from the velocity. If we stay on a straight path, our acceleration will be in the same direction as our motion. The basic theory of normal and tangential component. When a particle moves along a curved path, it is sometimes convenient to describe its motion using coordinates other than Cartesian. When the path of motion is known, normal and tangential coordinates are often used. In the n-t-coordinate system, the origin is located on the particle. Thus, the origin and coordinate system move with the particle. The t-axis is tangent to the path at the instant considered positive in the direction of the particle's motion. The n-axis is perpendicular to the t-axis with the positive direction toward the center of curvature of the curve. The positive and anti direction are defined by the unit vectors and ut, respectively. The center of curvature, O, always lies on the concave side of the curve. The radius of curvature r is defined as the perpendicular distance from the curve to the center of curvature at that point. The position of the particle at any instant is defined by the distance s along the curve from a fixed reference. Study case 1. A jet plane travels along a vertical parabolic path defined by the equation y equal to 0.4x to the power of 2. At point A, the jet has a speed of 200 mph, which is increasing at the rate of 0.8 mph to the power of 2. Find the magnitude of the plane's acceleration when it is at point A. The solution is at equal to v equal to 0.8 mph to the power of 2. dy per dx equal to d bracket 0.4 x to the power of 2 close the bracket per dx equal to 0.8 x d to the power of 2y per dx to the power of 2 equal to d bracket 0.8 x per dx equal to 0.8. At x equal to 5 km, dy per dx equal to 0.85 equal to 4. d to the power of 2y per dx to the power of 2 equal to 0.8. So p equal to bracket 1 plus dy divided by dx to the power of 2 close the bracket 3 divided by 2 divided by d to the power of 2y divided by d x to the power of 2 equal to bracket 1 plus 4 to the power of 2 close the bracket 3 divided by 2 close the bracket divided by 0.8. So the answer is 87.62 kilometers. Normal component of acceleration is an equal to v to the power of 2 divided by p equal to 200 to the power of 2 divided by 87.62 multiplication 10 to the power of 3 equal to 0.457 mph to the power of 2. The magnitude of the acceleration vector is a equal to bracket at to the power of 2 plus an to the power of 2, close the bracket, 1 divided by 2 equal to 0.8 to the power of 2 plus 0.457 to the power of 2, close the bracket, 1 divided by 2, so the final answer is 0.921 ampere s to the power of 2.
For the discussion in the first case, we have a jet plane travel along a vertical parabolic path, which is defined by an equation. From the equation, we can differentiate twice, since path s is time derived from velocity v and velocity is time derived from acceleration, to identify the tangential acceleration. After the differentiation, we can multiply the acceleration value at the x-axis to the path distance. Then, we can use the radius of curvature formula to find the radius of curvature value. Then, we can use the radius value to find the normal acceleration by using its formula. And lastly, we can find the magnitude of the acceleration vector since we have both of the normal and tangential components. And using the formula of the magnitude of the acceleration vector.
Study case 2. Given a car travels along the road with a speed of v equal to 2sm divided by s, where s is in meters, r equal to 50 meter. Find the magnitudes of the car's acceleration at s equal to 10 meters. The acceleration vector is a equal to at ut plus an un equal to v bracket ut plus v to the power of 2 divided by p, close the bracket, un. Tangential component, since at equal to v equal to dv divided by dt equal to dv divided by ds, multiplication ds divided by dt equal to v dv divided by ds. When v equal to 2s, at equal to d bracket 2s divided by ds, v equal to 2v. Ats equal to 10 meters, at equal to 40 ampere s to the power of 2. Normal component, an equal to v to the power of 2 divided by p. When s equal to 10 meter, an equal to 20 to the power of 50 equal to 8 ampere s to the power of 2. So the magnitude of the acceleration is square root 40 to the power of 2 plus 8 to the power of 2 equal to 40.8 ampere s to the power.
For the second case, we have the speed or velocity of the car, which was defined in a function. To find the magnitude of the car's acceleration, first insert the given path value into the speed or velocity of the car's equation. Then, we can find the tangential components by using its formula. After that, we can find the normal components using its formula, where r is the radius which was given in the first case, in the case earlier. After finding both tangential and normal components, we can use its formula to get the magnitude of the car's acceleration.
Study case 3. Given a boat travels around a circle path, r equal to 40 meter at a speed that increases with time v equal to 0.0625 t to the power of 2 ampere s. Find the magnitudes of the boat's velocity and acceleration at the instance t equal to 10 seconds. Plan the boat starts from rest v equal to 0 when t equal to 0. So the solution is the velocity vector is v equal to vut, where the magnitude is given by v equal to 0.0625 t to the power of 2 ampere s. At t equal to 10 seconds, v equal to 0.0625 t to the power of 2 equal to 0.0625 multiplication 10 to the power of 2 equal to 6. Next, tangential component, at equal to v equal to d bracket 0.0625 t to the power of 2 divided by dt equal to 0.125 t ampere s to the power of 2 at t equal to 10 seconds, at equal to 0.125 t equal to 0.125 bracket 10 equal to 1.25 ampere s to the power of 2. Normal component, at t equal to 10 seconds, an equal to 6.25 to the power of 2 divided by 40 equal to 0.9766 ampere s to the power of 2. The magnitude of the acceleration is square root bracket 1.25 to the power of 2 close the bracket plus open the bracket 0.9766 to the power of 2 close the bracket. Final answer is 1.59 ampere s to the power of 2.
For the third case, we have a boat that travels in a circular path with its radius value given. The speed of the boat was also given. To find the magnitude of the boat's velocity at a certain time, we need to identify the boat's velocity by inserting the time value in the boat's speed equation. Then, we can find the tangential component of acceleration by differentiating the boat's speed function, since acceleration is the time derivative of velocity. After that, we can find the normal component of acceleration by inserting the given radius value earlier in the case and the identified velocity value into its formula. And lastly, we can find the magnitude of the acceleration vector using both of the normal and tangential component of the acceleration into the formula of the magnitude of the acceleration.
Study case 4. Given the train engine at E has a speed of 20 ampere s and an acceleration of 14 ampere s to the power of 2 acting in the direction shown. Find the rate of increase in the train speed and the radius of curvature r of the path. The solution is acceleration tangential component AT equal to 14 cos 75 equal to 3.623 ampere s to the power of 2. Normal component AN equal to 14 sin 75 equal to 13.52 ampere s to the power of 2. The tangential component of acceleration is the rate of increase of the train speed, so AT equal to V equal to 3.62 ampere s to the power of 2. The normal component of acceleration is 13.52 equal to 20 to the power of 2 divided by P equal to 29.6 meter.
For the fourth case, we have a train engine at point E, which was given its speed value and acceleration value. To find the rate of increase in the train speed, we need to find the tangential and normal components of the acceleration. In this case, an angle was given. Therefore, we need to insert the angle value to find the tangential component and normal components of the acceleration into their formula. After that, we can find the magnitude of the acceleration of the engine train, since we have both of the normal and tangential component of the acceleration. Since tangential acceleration equals to velocity, the value of the tangential component is equal to the velocity. Lastly, we need to use the identified normal component by inserting its value into its formula for us to identify the radius of curvature.
Case study 5 given. Starting from rest, a bicycle travels around a horizontal circle path r equal to 10 meter at a speed of v equal to bracket 0.09 t to the power of 2 plus 0.1 t close the bracket ampere s. Find the magnitudes of her velocity and acceleration when she has traveled 3 meter. Plan the bicycle starts from rest v equal to 0 when t equal to 0. The solution is integration bracket 0.09 t to the power of 2 plus 0.1 t close the bracket dt as t equal to 0.03 t to the power of 3 plus 0.05 t to the power of 2. Calculate the time t when s equal to 3 m. 3 equal to 0.03 t to the power of 3 plus 0.05 t to the power of 2. T equal to 4.147 seconds. The velocity at t equal to 4.147 s is v equal to 0.09 multiplication 4.147 to the power of 2 plus 0.1 multiplication 4.147 equal to 1.96 ampere s. Tangential component AT equal to V equal to D bracket 0.09 t to the power of 2 plus 0.1t, close the bracket, divide by dt equal to 0.18t plus 0.1 ampere s to the power of 2 at, t equal to 4.147 second, at equal to 0.18, multiplication 4.147 plus 0.1 equal to 0.8465 ampere s to the power of 2. Normal component an equal to v to the power of 2 divided by p ampere s to the power of 2 at t equal to 4.147 as an equal to bracket 1.96 to the power of 2 divided by 10 equal to 0.3852 ampere s to the power of 2. The magnitude of the acceleration is a equal to square root bracket 0.8465 to the power of 2 plus 0.3852 to the power of 2. The final answer is 0.930 ampere s to the power of 2. Thank you.
For the fifth case, there's a bicyclist that was set to travel around a horizontal circular path with its radius given at its speed or velocity, which was defined by a function. First, find the position s of function by integrating the speed function, since velocity is the time derivative of position function. Then calculate the time t by inserting the position value into the position function. After that, we insert the identified time value into the velocity v function, and after that we can find the tangential component of the expression at. Since tangential component equals to velocity, we can only differentiate the velocity function and insert the time value into the new function for us to obtain the tangential component of the acceleration. Next, we need to find the normal component of the acceleration by inserting the velocity value and the radius into the formula. And lastly, we can find the magnitude of the bicyclist acceleration, since we have both of the normal and tangential component of the acceleration, and using the formula of the magnitude of the acceleration.
The conclusion is curvilinear motion is defined as the motion of a moving particle that follows a predetermined or recognized curve. The study of such motion implies two coordinate systems, the first of which is planar motion and the second of which is cylindrical motion. Moreover, we find that the direction of motion of an object can be determined by its velocity. Next, the velocity and acceleration of the object can be calculated using the normal and tangential component. In conclusion, curvilinear motion is a movement that often occurs in our daily life. For example, a car driving along a curvy road. If the steering wheel is not controlled according to the direction of the road, the car will run out of the road. Therefore, we need to know and master this concept so that it can be applied in our daily life.